Lab 4. So in this lab, we familiarized ourselves with circuits and using principles of the loop rule and energy of conservation. We predicted and observed the behavior of RC circuits along with measuring the conventional current and potential differences across resistors, capacitors, and batteries. So the first circuit we created was just with resistors. We found that on either side, the current was still the same at 0.02, and the calculated value for the current is relatively same to the value given by the program. If the ammeter was flipped, in the program it gave a positive, but in reality it could give a negative. And the recorded voltages across each resistor is right here. So if we did a whole loop through this circuit, then the potential difference would be zero due to the loop rule. And in addition, having the voltmeter attached to the circuit in parallel results in no altering of current because the resistor has a high enough resistance that no current will flow through. In comparison, if we had the ammeter in parallel, the ammeter has basically no resistance, and in the program it has no resistance, then the current will just flow through the ammeter as if it was a wire and not flow through the resistor, causing the current to change and increase. And to calculate the values of the resistance before we added the ammeter in parallel, we used V equals IR and changed it to solve for R to get each of these values. And of course, the wire ammeter in the program are ideal, so they have zero resistance. And in the bottom right corner is the image of the potentials across all of the circuit parts. So then in RC circuits, we did a 10 ohm and 20 ohm, same 0.2 farad capacitor. The light diminished with time because I goes to zero and the capacitor is being charged. The charging and discharging times were relatively the same. Of course, the 20 ohm took longer. And then for the 30 ohm, so we charged the capacitor with a 9-volt battery, set the capacitor ready to discharge, set up the voltmeter across the capacitor, and since it was a program, we could stop and start the discharging at any time we wanted to collect data. Here's the graph that we created. From the equation given in the lab procedure, we can see that equation is in y equals mx plus b. And so knowing that, we used the slope of the graph we created and just inverted it and multiplied by a -1 to get RC. So what if? If we were doing this lab in real life with the actual ammeter instead of ideal ammeter, what would be the difference? So a real ammeter has a small amount of resistance, and the total resistance of the circuit would be greater than predicted, resulting in a lower current than predicted and lower voltage data from each of the other true resistors, throwing our data off by a little bit. And if we were doing this lab in real life and had to use a real battery to charge a real capacitor with no resistor in the circuit, how quickly would our ideal model predict the capacitor to reach full charge? So in the ideal model, it would be a lot faster because in reality, a real battery has small resistance along with the wires connecting them. They all have a small amount of resistance and heat loss. And so in the simulation where everything is ideal, then there would be no resistance or heat loss and it would go much faster compared to reality.